Okay, picture this. Imagine a single machine so massively scaled that it stands 10 stories high and literally spans the width of 3 entire football fields. Well, that is the actual footprint of the laser at the National Ignition Facility. It's an absolutely staggering piece of engineering, built to harness light on a level that practically defies belief. Welcome to today's Explainer, where we're going to unpack the completely fascinating world of laser technology. We are taking a journey from the microscopic quirks of quantum physics to incredibly delicate, life-saving medical procedures, all the way to raw, heavy industrial power. It's really just an incredible story of scientific evolution.
Okay, let's dive into this. Here is our roadmap for the explainer. We'll start with decoding the acronym, then go inside the cavity, look at the 5 families, explore modern medicine, check out industrial power, and finally peer into the future. So, Section 1, decoding the acronym. What does laser actually mean?
To really appreciate what lasers can do today, we first need to understand the word itself, because laser isn't just some catchy name, right? It's actually a very literal description of a physical process. LASER stands for light amplification by stimulated emission of radiation. Now, the absolute crucial point here is that foundational word stimulated. Basically, in optical materials, think certain glasses, crystals, or gases, we have atoms with electrons. When you pump those atoms full of energy, like from an electric current, those electrons get excited. They jump from their normal ground state up to a higher energy orbit. But they don't want to stay there. When they drop back down to normal, they release that extra energy as a little particle of light called a photon. By stimulating this emission, we can actually take control of that light. Moving right along to Section 2, inside the optical cavity. So we know how to make a photon, but how do we turn that into a powerful, focused beam? Well, that happens inside something called the optical cavity, through a really precise 4-step process. First, our energy source excites the electrons in our active gain medium. Second, they drop back down, emitting photons. Now, step 3 is where the magic really happens. We place mirrors on either end of this medium. The photons bounce back and forth between these mirrors, and as they travel, they strike other excited atoms, stimulating them to release their own photons. And here's the crazy part. These new photons are essentially exact clones. They travel in the exact same direction, at the exact same speed, with the exact same wavelength. Finally, in step 4, the number of clone photons becomes so massive that they just pass straight through one of the mirrors, which is designed to be only partially reflective. That escaping light? That's our laser beam.
You know, the scientists at the National Ignition Facility describe these cloned photons perfectly. They call them synchronized members of a marching band in the Rose Parade. It makes so much sense because unlike a regular light bulb that just scatters mixed, messy wavelengths of light in every possible direction, a laser produces a coherent beam. Every single light wave is marching in perfect lockstep. And that unison is exactly what gives the laser its incredible power, allowing it to stay sharply focused over vast distances. I mean, literally to the moon and back.
All right, Section 3, the 5 laser families. Now that we know how they work, let's categorize them. The gain medium we just talked about, that stuff trapped between the mirrors, actually dictates the exact type of laser we get, and even the color of the light it produces. There are 5 main laser families. Gas lasers, like CO2 lasers, are these massive workhorses often used for heavy industrial cutting. Solid-state lasers use crystals or glass, kind of like the original Ruby laser. Then you have fiber lasers, which are a highly efficient offshoot where the medium is an optical silica glass fiber. Liquid or dye lasers use organic dyes and can actually be tuned to different wavelengths, which makes them awesome for spectroscopy. And finally, semiconductor lasers, or laser diodes. These are the tiny, highly compact lasers you interact with every single day. They power everything from the barcode scanners at the grocery store to your old CD players. The contrast in scale across these families is just wild.
Now, across all those families, lasers basically operate in 2 different modes. Continuous wave lasers provide a constant, uninterrupted flow of energy. Just think of a standard laser pointer. Pulsed lasers, on the other hand, interrupt the beam at regular intervals. Why would we do this? Because it allows the energy to build up before release, achieving massive peak power. To put that into perspective, a continuous wave laser might run at a steady 6,000 watts, but a small 100-watt pulsed laser can release rapid-fire pulses that peak at 10,000 watts each. That incredibly dense burst of energy is absolutely critical for highly precise applications. And this brilliantly illustrates our next topic, Section 4,
Lasers in modern medicine. When you can control light's wavelength, power, and pulse duration with pinpoint accuracy, you can perform literal microscopic miracles on the human body. This comprehensive map from the Yoon Lab shows the sheer variety of these light-tissue interactions. On the left side, we're using light scattering and absorption for non-invasive diagnostics and imaging. But as we move to the right, increasing optical fluence and exposure time, we enter the realm of surgery and therapy. We can induce photothermal heating to literally vaporize unwanted tissue. We can use photomechanical shockwaves to safely fragment kidney stones, or even trigger photochemical reactions to activate targeted drugs. It's amazing. A perfectly relatable example of this is LASIK eye surgery. This procedure relies on an argon fluoride excimer laser emitting deep ultraviolet light at exactly 193 nanometers. Instead of burning tissue, these UV photons literally break the peptide bonds of collagen fibers in the cornea. It is so unbelievably delicate that a single pulse removes just 0.25 micrometers of tissue. That is roughly 1/400th the thickness of a human hair. This allows doctors to flawlessly reshape the eye without damaging any of the surrounding areas. And the precision goes even deeper inside the body. Get this, if a patient needs a cardiac pacemaker wire removed from a delicate coronary blood vessel, doctors use a specialized xenon chloride laser. They thread a fiber optic sheath right into the vessel, and short nanosecond laser pulses vaporize the tiny amounts of scar tissue binding the wire. It causes a localized ablation of just 100 micrometers of tissue directly in front of the tip. It safely frees the wire from the super delicate blood vessel wall with basically zero collateral damage. Now for a complete change of pace. Section 5, Industrial Power, Cutting Steel. So from microscopic medical precision, we are jumping to the exact opposite end of the spectrum, raw, unadulterated industrial power. When it comes to cutting thick steel, conventional wisdom used to say that plasma cutters were the only economical choice. But high-power fiber lasers have completely flipped the script, and it's largely because of this massive number, 100. Advancements in the pump diode technology that powers these fiber lasers increased electrical efficiency from around 20% to roughly 70%. Combined with massive leaps in single-emitter power, the cost per watt of a fiber laser has plummeted by a factor of 100.
Now, what's really interesting is how that efficiency translates to the actual factory floor. Look at this data comparing a 40 kilowatt fiber laser to a 300 amp plasma cutter cutting through 20 millimeter thick mild steel. The fiber laser is operating at twice the speed. So for the exact same monthly operating cost of about $20,000, the laser is outputting 38,000 meters of cut material compared to the plasma cutter's 19,000 meters. One laser machine is literally doing the work of 2 plasma cutters.
But the return on investment isn't just about raw speed. Fiber lasers are completely dominating metal fabrication because their cuts are fundamentally cleaner. They produce a much smaller heat-affected zone, meaning the edges are often immediately ready to be welded. There's practically no need for costly, time-consuming secondary operations like grinding or edge cleanup. When you factor in the ability to cut really complex geometries and save valuable floor space, the high-power fiber laser is just an absolute game-changer for heavy industry. Which brings us to our final section, number 6, the future of light. We've seen how lasers shape steel and heal our bodies today, but where is this technology actually heading? Let's turn to the cutting edge. Researchers are currently developing technologies that sound straight out of a science fiction movie. We're moving beyond bulky external laser machines to fully integrated photonics. Imagine biomaterial waveguides made of biodegradable silk that can deliver therapeutic light deep into the body and then just safely dissolve. Or, even crazier, consider cell-based lasers, where cells are loaded with tiny intracellular microlasers. These laser-equipped cells could actively seek out sites of inflammation or tumors from within the body, emitting coherent light for highly multiplexed imaging and incredibly targeted therapy. No way, right? It really makes you step back and wonder. We started this explainer with a laser the size of 3 football fields, and we're ending with lasers small enough to live inside a single human cell. With lasers evolving from those massive 1960s prototypes to these microscopic, intelligent biological tools, how else will we harness the power of synchronized light to transform our future? Thank you so much for joining me on this exploration of the explainer material. Keep questioning, keep learning, and I'll catch you on the next one.